Hooke's law is all to do with the elastic potential energy store. Through this lesson, we're going to look at the words elastic, the word deformed. We're going to go through the required practical, and we're going to be able to use Hooke's law in the form of a triangle. Two key terms, elastic and deformed. When something is elastic, it can be stretched and it will go back to its original form. When something is deformed, you stretch it and it cannot return back to its original form. We say it's past its elastic limit. We need to know the variables in this practical. The independent variable, what we're changing, is the force added each time. So we're adding 0.1 kilograms or 100 grams, which is equal to 1 Newton. So what we're actually changing is the force. Force is the independent variable. The dependent variable is what we're recording. We record the length, but ultimately the extension. So we're recording the extension. Extension is our dependent variable. And finally, we need to look at some control variables. There may be more than these, but these are two that I've selected. We're using the same spring each time, and we're using the same ruler for measurements, because imperfections in the ruler, different rulers, could lead to false results. For Hooke's law, you'll need to know the practical, because sometimes you're asked to give a method. We're obviously going to be looking at the length of the spring and the extension of the spring. We'll be using masses. Now these masses all add up to 1 kilogram. We're going to be adding 100 grams at a time. 100 grams is equal to 1 Newton. Okay, so we'll be adding 1 Newton masses to this every time. Okay, what we've done here is we've clamped a meter ruler. It goes off the edge of the desk because the spring might extend beyond the length of the desk. So we need to have measurements for that. At the top here, I've already put a spring. Now the first thing we need to do is we need to measure the length of the spring from here to here. Okay, so just that part there, not the two circles at the end, just the spring itself. So what we do is we measure that. I'll measure this one actually because it's already hung up. I can see that that's 2.2 centimeters. So in any table I would write down 2.2 centimeters. The next step is to add a mass. So remember, we're adding 100 grams, 1 Newton. Now if you notice, the spring extends, it stretches. What we need to do is keep measuring the lengths. We're not measuring the extension at the moment, we're just measuring the length of the spring. So when we add 1 Newton, we've got 5.6 as the length. When I add a second Newton, so 200 grams, the length of the spring increases. It's gone up to about 8.8 centimeters. Add another 1 Newton. It extends further. I've done this practical with a different spring and found these results. So we know that the force added is always 0.1, 1, 0.2, 2, 0.33, and so on. The length was calculated, and we could see that as we increased the force, the length increased. But we're looking for something called extension. To calculate extension, you just minus the original value away from your length at each mass added or force added point. Okay, so in the first one here, we'll do 6.0 minus 2.3. Second one, we'll do 9.5 minus 2.3, 13.0 minus 2.3, and so on. We end up with some results that look like this. Okay, so as we increase the force, extension also increases. Usually the results are put into a graph with extension on the y-axis and force on the x-axis. We say that this line is directly proportional. If we double the weight, the extension should double. If we triple the weight, the extension should triple. But if you look at this graph carefully, the trend line changes. Now this point here is the limit of proportionality. Okay? After this point, doesn't obey Hooke's law anymore. We call this area inelastic. The spring has been deformed. This means that if we try to stretch with a a weight of 2 newtons, we would not get the spring back to its original form. The triangle for Hooke's law is F equals KE. So force at the top, K and E at the bottom. Okay, so this thing here is probably new to you, it's the spring constant. We work this out by doing force divided by extension. Okay, the force has to be measured in newtons, extension has to be in meters, it can't be in centimeters. So if answers are given in centimeters or kilometers, we need to convert them to meters before we use the triangle. And the unit for spring constant is always newtons per meter, or N/m. Just like with any other equation, we'll draw the formula triangle first. So we know it's F at the top for force, that's measured in newtons. K over here, spring constant, measured in newtons per meter. And we've got our extension over here. Okay, so if we're trying to work out this answer, we would do the underlining first. So we know the spring constant is 300, and we know that the extension is 0.01. Remember, we always do it this way with F, K, E. This way we'll guarantee the marks. So extension 0.01 meters. Spring constant 300 newtons per meter. So if we're looking to find force, cover up force, it's spring constant times extension. So spring constant times extension. If we work this out on the calculator, we should have 300 times 0.01. That gives us an answer of 3 newtons.